okay? You alive? Barely. Awake? Thank you. Need a hug.
It's kind of really bad.
It sounds like it. It looks like it. Hey. Oh, you can turn it out. I just got a new one.
Okay.
So,
It was one packet?
correct. It was number, it's the
I tried
fourth
to
one.
print it out before I got here, but my printer was working 4 hours.
Yeah, gotcha. Happens to me all the time. Thank you, sir.
Thank you.
I'm holding these hostage for no good reason. Somewhere.
Someone.
Yeah. Thank you, sir.
Okay, I thought I put in there, but I wasn't sure.
I'm hiding them all. Thank you, ma'am. I'll save them for you. Oh, it's already stapled.
Right there. I wanted to look at things.
Still doesn't really matter that much. Actually, I already did it. Oh, no, that's not you. I'm sorry. I completely forgot that you took that, so I'll put it right today for you. So,
Oh,
sorry
yeah.
about that.
Thank you.
I noticed that there was some integration by part at the top there. When you took the picture. Right. Oh, yeah, yeah, yeah. All that fun calculation. Suffering. The two worst courses I took as an undergrad was Calc 2 and operating systems. Operating systems was the worst. The teacher I had, the other teachers called her the Dragon Lady. So it's kind of bad when the other teachers called with other teacher names.
What was your undergrad focus?
Computer science.
And operating systems is horrible?
Yeah.
Is it normally horrible, or is it just your teacher?
It was the teacher. First class, 100 PowerPoint slides. Deadly serious. 50-minute class. I said, I'm not good at math, but that's basically a little bit more than 1 slide per minute. And she's like, you're right. And then she just kept on going.
That's how computer science is.
Yeah. It's like, why even bother? You're not going to learn anything. Like looking at a slide for 50-some seconds. Oh, well. You're wrong.
You just felt like.
I'm tired of this.
I'll take it. You don't.
You got that new press.
Yeah. Well, they're gonna play in me.
Yeah, someone keeps moving through different. They would have.
Donnie, I just said I was gonna take that. Walk it up. I'll staple it for you.
Thank you. There are 2 of them.
Extra. Shell can have it. I did that on purpose.
Really?
Absolutely. Pass that back to Andre. Andre will pass that back to Robert. There we go. It's an efficient algorithm.
Coordination.
Check that out.
On the computer, you had to like do that, like just skip through all the numbers.
Can't just go in linear fashion.
Doesn't work.
No.
Kind of that was an array.
I was about to say you could access from an array that way.
But that would take several lines of code. You can't just like tell it to do that lines of code.
No, it's not smart enough to do all that stuff. Okay, so we will press on with direct proof. Sounds like fun, right, guys? Maybe not. Thanks, Ryan. Just something up for us. All right, so we're going to take a look today at Quotient-Remainder theorem, which is going to lead us into the idea of being able to do proofs by division into cases. Okay, and then after we start looking at some of that stuff, we'll start looking at maybe some of the floor and ceiling stuff. Okay, so we're looking at our next assignment. So assignment number 5. That's going to be due on Monday, what's that, the 10th?
Mm-hmm.
I guess so, today's the 3rd. Okay. So if you guys have questions while you guys are looking through that, make sure you email me so that way I can answer those questions for you guys. Okay? All right, did I miss anybody with the packet, or everybody got a copy of this? Good enough. Okay. So I want to start with something called the Quotient-Remainder theorem. Okay, that's going to lead us into being able to do the division into cases. The Quotient-Remainder theorem says that if there's 4 integers, n, d, q, and r, all right, there exists a unique q and r, so that if I defined an n and a d, you could write that integer n in this form, dq plus r. So basically, we would have to find what the value of d is and what the value of n is, or sorry, the value of q and what the value of r is, to be able to satisfy this Quotient-Remainder theorem. Okay, so I'm going to give you guys some of the stuff for this, and we're going to be able to do it. Okay, they're just number trick problems. They're not difficult. And then we're going to see where we would ever use this sort of thing in real life. Okay, not that any of us would ever use this in real life, but we can pretend. Okay, so the first thing I have is that I give you that n is 31 and d is 5. Okay, and we have to go under the assumption that there exists an r and there exists a q, such that this should actually be q here, guys, not d. Or I'm sorry, no, that's correct. So there has to be any value q, and it has to satisfy the d for this. Okay, so 31 is equal to 5 times q plus r. Okay, so that's what we're given. And basically what we have to do is we have to find a value of q and a value of r, such that r is between 0 and 5 in this case. Okay, it could be 0, but it can't be 5. So does somebody think they might know the values of q and r that would satisfy the Quotient-Remainder theorem? It should be pretty easy. So it's like,
Q could be 6 and R could be 1.
in fact, it's the only pair it could be. Very nice. Okay? The only way that this could be satisfied is 6 and 1. Okay? Now, how come we can't use something like 5 and 6? Because we know that 5 times 5 is 25 plus 6 would be 31. So why couldn't we use 5 and 6 for q and r respectively? Go ahead.
6 is bigger than 5.
Right, because we can't have an r that's bigger than the d remainder there. Very good, Don. Okay?
So do you have to do all the time like trial and error in this thing?
Well, basically trial and error is going to be the easiest way to do it, okay? What I always think of is like a div and mod, and think so that your modulus is going to be between d and r. Or I'm sorry, 0 and d. That's probably the easiest way to do it, okay? So just think of your multiplication tables to do it that way. Okay? Like for instance for b, okay, we know that 109 is equal to 13 times some number plus r. So once again, we just have to define what q and r are. Okay? So what you might want to do is just do 109 divided by 13 and figure out what the remainder is. So that way you don't have to do too much work.
Okay.
Okay? So guys, does anybody think they might know what q and r are respectively for this one?
So Q is 8.
Okay? So q would be 8, because 13 times 8 is going to be 104. And that would have to mean that r is what, guys?
5.
It has to be 5, right? So probably the easiest way to do these problems is to just take 109 divided by whatever d is, and then just say, okay, well, how many more do I need to get to 109 in this case? Okay, so that's all there is to it, guys. It's not difficult, okay? So does that help maybe, Art, with that, like eliminating a trial and error method?
Yeah.
Okay. For this last one, we have negative 79 is equal to 8q plus r. Okay, now, typically this is what I'll see that's not correct. Okay, so I'll see that q is negative, oh, I'm sorry, I'll see something like this, I apologize. I think I just wrote the answer on the board, which wouldn't be good, so. But typically I'll see something like this, where somebody might write something like -9, and then they might put in something like 9 or something like that, okay, or 7, sorry. Sorry, -9 and 10. No. Anyway. I keep trying, now I'm thinking of the wrong answers, and I can't think of the wrong answers. All I can do is think of the right answer. Sorry, that is a bad thing, because I guess you want your teacher to know the right answer. All right. But with these types of negatives, what you want to make sure of is that you just go over a little bit, because remember, R has to be bigger than 0, okay? Like typically what I might see, now I'm thinking about it, I might see something like this, -9, and then -7. Okay, that's what I was thinking of. That's the one that I always see students do. And unfortunately, you can't do that because R has to be bigger than 0. Okay, so don't do that. I probably just confused you guys. Yeah, I probably just confused you guys by thinking of wrong answers. So for this time, it has to be -10 and 1 would be the right answer for this, okay? So with negative numbers, just go a little bit over, and then think of your R to add it back into that, okay? So does that make sense, guys? Any questions about that? Not meant to be too difficult. Okay. One of the things that the quotient-remainder theorem allows us to do is that sometimes, especially in computer science, we have to try to write numbers in specific forms. Okay, I'll show you guys an example of what I mean later. But if I give you guys a specific value for D, okay, there's only a finite number of cases that satisfy the given conditions. Okay, so I say use the quotient-remainder theorem defined by n equals dqr, list all the possible cases. Okay, so if D is equal to 3, okay, I think that there's only 3 possible cases that we could construct that would satisfy the quotient-remainder theorem. Okay, so does anybody think they might know what the 3 possible cases might be for this? So R would have to be 0, okay? Because remember, we said that R has to be, what do we say, 0 less than or equal to R less than D, correct? So that would be 3 times Q plus 0, right guys? That's one of the cases. Does that make sense, guys? Because R is dependent upon the value of D. What's another possible case? Yep, 3Q plus 1, good. And then the final case would be 3Q plus 2, right guys? We can't have 3Q plus 3, how come?
Because it's less than D, not
Yeah, we have to make it less than D. We have to make R less than D, not less than or equal to. Okay, so when I say list out all the possible cases, if D were to be 3, these would be the 3 possible forms of the quotient-remainder theorem. Okay, and like I said, later in today, I'll show you guys why you might want to know something like that. Okay, so knowing that, we might be able to write letter B. Okay, so does somebody think they might know what the possible cases might be if D were to be equal to 5 in this instance? Or maybe not.
5Q plus 0.
Okay, so N would be equal to 5Q plus 0, good. And then, John, you want to go ahead and do the other one?
5Q plus 1, 5Q plus 2, 5Q plus 3, 5Q plus 4.
Okay. Sorry, I can't write as fast as you speak. Not that anyone can read it anyway. Okay. So basically, guys, whatever D is, that's how many possible cases there are. Okay? Now, I'm not asking you guys to find a specific number. I'm just saying write out the possible outcomes for this. Okay? And like I said, later today, when we do a problem that involves quotient-remainder theorem, the first thing you guys have to know is how many possible cases there are for the outcomes. Okay? So does this make sense, guys? Basically, whatever D is, that's how many cases there are, and you start at 0 and you go up to that number, but don't include that number. Okay? So for instance, if I said 2, you would just have 2Q plus 0, 2Q plus 1. Okay? Or in other words, even and odd, right guys? Because that's the definition of what if D were equal to 2. Alright. In fact, we're going to do that a little bit today. Okay, so one of the most useful methods of proof is sometimes that if you don't necessarily have a definition for something that's nice, sometimes you can exhaust all the possible cases. Okay? So division into cases is one of the most useful ways to provide or to prove universal statements, okay, if you can't utilize a definition. Like for instance, if I just say for all integers, okay, well that's kind of difficult because we don't necessarily have a definition for integers. But isn't it true that all integers are either even or odd, right? They're either positive, negative, or zero. So we might be able to use that division into cases, okay? Just an example of where you guys have probably used division into cases, but you don't remember it, okay? In Calc 1, okay? You don't have to copy this down, by the way, but how many of you guys remember this animal, the intermediate value theorem, okay? If you don't, just shake your head and lie to me that you did, that's fine, but and you guys, yeah, that's right, good lie, Greg, I appreciate
F
that.
of b minus f of a by divided by b of a, that...
Not quite, okay? If I have a function, you're on the right track, but the intermediate value theorem says if I have a function, okay, a continuous function, all right? And we're not going to prove this, by the way. But let's say that you have a point f at a, which is less than 0, and this is point A, and you have a point B, and f at b is bigger than 0. Okay? What does the intermediate value theorem guarantee?
There is a point between a and... in the middle that's between a and b, right?
There's a point in the middle that specifically does what?
Equals 0.
Is a 0 in a function. Right. That means, by the intermediate value theorem, that there is some point f at c which is equal to 0. Okay? That's the intermediate value theorem. All right? The three possible cases are that this number is less than 0, this number is bigger than 0, or this number is equal to 0. All right? And I don't know how many of you guys remember doing this, but maybe your teacher proved the intermediate value theorem, and there's actually 3 cases to prove that. Okay? So if you ever want to, just go in your calc textbook. The proof is literally like this long. It's a very short proof. But that's somewhere in real life mathematics that cases would be utilized. Okay, so I didn't want you guys thinking that, like, you know, division into cases is just one of those oddball things. It's actually used quite often. Okay, so any questions about like intermediate value theorem? By the way, if you're running a computer program, the intermediate value theorem is really important because what if there is no 0? Then it goes into an infinite loop, right? So one of the first things a computer programmer might do is just to make sure that the 0 exists. Then you can run your algorithm to try to find it. Okay, so that's where I remember utilizing the intermediate value theorem. All right, anyway, besides all this calculus crap. Okay, so the 3 types of different types of cases of integers are the main 2 I'm going to ask you guys to utilize. I'm not going to ask you guys to do positive, negative, or 0, but I'm going to ask you guys to be familiar with even and odd cases or the form by the quotient-remainder theorem. Okay, which is why I just demonstrated what we just did. Okay, so division into cases is actually very similar to the stuff that we've already been doing, except we're going to do it twice instead of just once. Okay, so if I ask you guys to prove something by division into cases, you define your variables just like we did in the previous type. Then what you guys want to do is just write out all the possible cases and then prove each case. If the original is true for all the cases, then you can say by case 1, case 2, case 3, case however many cases there are, the original statement is true. Okay? All right, so what I want to do, guys, I want to start out with a really basic example of division into cases, okay? And then maybe give you guys like 1 or 2 to practice, okay? This is a very typical type of problem where division of cases is used, okay? So I want to prove the following, okay? I want to prove that for all integers x, okay, that such that x is an integer, I want to prove that this structure right here is always odd. Okay? Now, before we even start the proof, what's the first thing we might want to do?
Define them.
Yeah, let's let x be like some sort of number, right, guys? Because what if it's not true? And we just go through and do the proof for like 20 minutes. Well, we just wasted 20 minutes of our lives, right? We don't want to just assume it works, even though in our class it's probably going to work. Okay? So let's just go ahead. You don't have to write this down, but what if x equals 0, guys? Well, don't we just get positive 3? So then the output is 3, which is certainly odd. Okay? So it works for 0. Okay? What if x were equal to 2? Let's use an odd number, but not 1. Because I think if we use 1, we get 3 out of it again. So let's say x were to be equal to 3 for some reason. Okay? If x is 3, we get 9 minus 3 plus 3, which is 9. Right, guys? So, just by using a couple basic numbers, we can obviously see that it looks like it's going to work. Okay, so that might be your first step. And I know it takes like maybe 20 seconds to do this, but it's better than wasting 20 seconds than wasting 20 minutes doing the proof. Okay, and I'm just trying to get you guys to think, when you do it in real life, this is what you guys might have to do first, is just check with trivial cases to make sure it works. Okay, so here's our proof. Okay, guys, there's only one variable. Okay, so, this is another one already. So let's start by saying, let's let x be an element of the integers. Okay, sounds like a good idea. And you don't have to, but you can say arbitrary but particular.
Aren't you going to write step 1, step 2 on this one?
Oh, you can if you want to, but because it's division into cases, and because we already know step 1, 2, etc., we should be okay with that.
Okay.
But you can go ahead and label it. Now, what do we usually do, guys? Don't we use some sort of definition?
Mm-hmm.
The problem is there is no definition for integers, right, guys? I mean, we know that's just a whole number, either positive or negative or 0.
We do have z odd, 2k plus 1.
Well, that's odd, and then
So you have to use the definition for an even and an odd.
right, so we have to show it once true for even, once true for odd. And guys, isn't it true that every number, every integer, exhibits either even or odd pairing? Okay? If you guys think of any integer, it's got to be even or odd. Okay? So here's what we're going to do. And again, I'm going to put this in brackets. You don't have to write this. But we are going to divide into even and odd cases. Okay? And guys, most of the time when you're doing integer proofs, even and odd is the easiest way to do it. Okay? So my suggestion would be, like if you're in a class and you have no idea where to start with an integer proof, start with even and odd. I mean, there's only 2 possibilities. Okay? So now what we're going to do is we're going to do the proof itself. Okay? So this is case 1. Okay? So case 1 is where x is in z even. So, here's how we're going to start this. We're going to say, let's let x be in z even. Okay, so you have to define x to be an even variable. We've never done that. We're just saying right here that that's the case. So, let's let x be an element of z even. Okay. What can we say about x then?
By definition, x is equal to 2k.
Sure. Or k is an integer.
2k is an integer.
So, by definition of even, x is equal to 2k, or k is an integer. Okay. So that looks good to me. Just like you guys did on your homework, or just like you guys did in class, okay? What's the next thing we generally do after we define the variables? Substitute, right guys? That's exactly what we're going to do. We're going to substitute 2k back into the original statement that we're trying to prove. So by substitution, x squared minus x plus 3 is going to be equal to quantity 2k squared minus 2k plus 3. Okay, so let me get out of your guys' way, make sure that's okay. Yeah, this is a pretty easy proof. We've done this several times with integer stuff. I bet you guys probably already know what the next step is without thinking about it. So what is your nose or what's your intuition telling you to do at this point? Besides go home.
By multiplication.
Yeah, just square out the 2k, right?
Yeah.
So just square it out. I mean, that's what you guys would do like in real life. So now we're in math life, might as well do it. Because math life and real life aren't the same thing. So doesn't this become 4k squared minus 2k plus 3? And that's just by multiplication. Or exponent rules, power of a product rule. You know, I'm pretty flexible with the rules, okay? As long as you don't put like puppy dog tail or something like that. Alright, what are we trying to show with 4k minus 2k plus 3? We're trying to show
It's
that
even.
that it's not odd,
Odd,
right? Because remember at the beginning we said it's odd. Okay?
But we're doing this case one is for even, right?
Well, no, we let x be even.
Oh, okay.
But remember, we're trying to show that the original result is odd. Okay?
Oh.
So this one, we're letting the variable be even. Does that make sense? Art?
Gotcha, gotcha.
Okay. So, does anyone, what's the form of
Four
odd,
kids.
by the way, guys? 2k plus 1. Okay? So we're really close, but I think that 3 is kind of throwing some of us
So
off.
2 plus 1.
Go ahead.
So you rewrite it as 2 plus 1.
Yeah, we could just rewrite 3 discretely because it's 2 plus 1, right? Nice. So just by some basic computation, and we've seen this before, right guys? We did this trick. We can rewrite this, since 3 is 2 plus 1, which I highly doubt anyone in here doubts, but if you do, let me know, because then I'll be scared for your safety. Andre, that's not a good thing. I'll give you a hug later. And guys, isn't it obvious that we could factor a 2 from those first 3 terms, right? And then we can just use closure and we're done, right? This, I mean, it's just so obvious, okay? So we're going to factor a 2. I'm going to write the steps in at the end, by the way, okay? So 2, when we factor a 2 from the first 3 terms, 2k squared minus k plus 1 end quantity plus 1. And then finally, guys, couldn't we say something about 2k squared minus k plus 1? We can make that equal to p, m, whatever letter you want, as long as we haven't reused it. So this is going to be equal to 2p plus 1, where p is an integer. If I were to fill in the steps, okay, the one after multiplication, that's just computation, okay?
Would we have to write that computation?
Did you write something different?
No, I didn't write anything yet.
Yeah, you have to justify the step, okay, because it is a proof.
Computation's pretty broad, right? You're saying that that's just like a...
When I say computation, computation is like number operations, okay? So it's basically like if you're, whenever you hear the word compute, that means you're simplifying an arithmetic statement, or making it more complex, if you would.
So could I write computation for the multiplication?
It's more algebraic, but yeah, sure, if you wanted to write it, that's fine. All right, so this guy right here is GCF, and then this guy right here is closure. Okay.
GCF applies with 2 variables. There's only 1 variable, right?
Wouldn't that be factoring QCM?
Well, we factor out the greatest common factor. So if you wanted to write factoring, but you really are, yeah, we have 2 different, well, it's the same variable, but since they're not like terms, there still is a common factor between those. Okay? If you just want to write factoring, that's fine too. Okay. All right. So guys, any questions about this one, guys? Okay.
Can you like skip the one computation step and just go straight to the GCF?
Yeah, that's fine with me. Okay. I just want to make sure when people go home, it's like, oh, how did that all of a sudden become that? Okay. Saves me a little bit of headache. All right. Other questions, guys? All right. So good news is we proved case 1. Bad news is we haven't yet proved case 2. That's what we're going to do next. Okay.
So do we have to write on the end of this by blah, blah?
Nope, because we're going to do that at the very end to save ourselves a lot. That's all right. That's a good question. Okay. I'm trying to make this as efficient as possible. We'll say that, which is just a nice word for lazy. All right. So now we're going to do case 2. And this time, case 2 is where x is an odd integer. Okay. We're going to do the exact same thing, except now we're going to define x to be 2k plus 1. Okay. So we're going to say let's let x be an element of z odd. Okay. By definition of odd. X is equal to 2k plus 1. Okay? Where k is an integer. And guys, the steps are going to be almost identical. It's just going to be a little bit of algebra difference in there. Okay? So what was the next thing that we did after we defined x to be even in the previous proof? Substitution, right? So by substitution, yeah. So by substitution, we're going to say that x squared minus x plus 3 is now going to be equal to the quantity of 2k plus 1 squared minus the quantity of 2k plus 1 plus 3. Okay? And notice, guys, every time I substitute everything, I utilize a parenthesis, especially if there's more than one term. Okay? It wouldn't be completely wrong, okay, if you guys, you'd still get the right answer. It would still be mathematically wrong if you forgot the parenthesis around the second step, okay, because there's a negative that has to get distributed there. All right. So, at this point, guys, what do you think the next step might be to be able to prove that this thing's odd?
Multiplication.
Yeah, FOIL everything out, right, guys? We have a lot of stuff to distribute, okay? So, by multiplication, now be careful. This guy right here, that's not 4k squared plus 1, right? Okay. What does this animal expand into?
4k squared plus 4x plus 1.
4k squared plus 4k plus 1, right, guys? That's okay.
Yeah.
That's all right. No big deal. I bet you wrote k.
Yeah, I wrote.
That's okay. No big deal. You were just thinking of the expanded binomial. Okay. What if you don't remember that? Okay. What's the easiest way to remember, like, how to get to that thing? Like, just in case you don't remember, that's the proper expansion.
Write it out twice.
Yeah. If you guys don't see that, what you guys do is you just write it as 2k plus 1 times 2k plus 1, and then you just do your FOIL, 4k squared plus 2k plus 2k plus 1, and then clearly that's 4k squared plus 4k plus 1. Okay? So remember, guys, if you're not good with your basic algebra like that, you can always beat it up by just doing the basic expansion of that.
What about Pascal's triangle?
What's that? Or you could use Pascal's triangle if you're good with that. So I'll never ask you to do a cubic though, so don't worry about that, or a quartic. We're going to distribute the negative, so that's minus 2k minus 1 plus 4. Okay? So it's just by multiplication. Notice if you forgot the parentheses, you would get minus 2k plus 1. You'd still get the right answer, but it would mathematically be incorrect. Okay? What seems almost like it's beating you in the face for the next step? Yeah, like terms. All right, I mean, if we don't know that, then, oh boy, that's bad. But you guys know that. So by combining like terms, I believe 4k squared plus 2k plus 3, right guys? Just regular old polynomial goodness. Guys, doesn't it look almost identical to the previous, except instead of a minus 2k, we have a plus 2k. We can use the exact same trick where 3 is 2 plus 1. Okay, so we're almost done with this animal. So this is going to be equal to 4k squared plus 2k plus 2 plus 1. Okay, again, that's just by computation. We can factor out the 2. Okay, so just by GCF. Twice the quantity of 2k squared plus k plus 1 and quantity plus 1. Right. And just to make it really easy on ourselves, I'm going to reuse the same variable. Okay, so instead of 2k squared plus k plus 1, I'm going to say by closure that's p. Okay, so just by closure, that's going to be equal to 2p plus 1. Okay, so let me give you guys a minute to copy all the algebra stuff down and make sure that's all okay. All right. I do want to explain why it's okay in this instance to reuse variables, because I bet you some of you guys are like, well, before you said let's not reuse variables, and all of a sudden now it's okay to do that. Okay. But are the algebraic steps okay, guys? I mean, nothing in there is past Algebra 1. Hopefully not too difficult. All right. Let me ask you guys this question. Why is it okay for me to reuse variables going from case to case? So, go ahead, Ryan.
Because they're not related.
Because they're not related to each case, right? One case is odd, one case is even, okay? It's almost like if you guys are programming a subroutine, right? You have global variables and you have local variables, okay? So these are basically your local variables when you're defining case 1 and case 2. The global variable in this case is this guy right here, okay? So just trying to relate it as much as I can to computer science, since it is required for computer science majors. I just want to make sure, like, you guys see that there are connections between those. Okay. So, everybody good with this stuff up to this point? Just one more thing to do. Okay? Last thing we're going to do is say by case 1 and case 2, so this would be like our step 3. So by case 1 and 2, we see that x squared minus x plus 3 not good enough. There we go. Is equal to 2p plus 1. Okay. Both of those were equal to 2p plus 1, which is why I like to reuse the variables so that we don't have to say equal 2p plus 1 or equal 2m plus 1. Just makes it easier for us.
Would it always end up like that, where the two have the same?
If it's true. Yep.
Okay.
If it's not true, then you just use like the counterexample over here, you might find that. But yeah, you can always manipulate it so that you get it to be the same form. Okay? And that takes a little bit of foresight. And that's why I'm trying to show you guys to reuse those variables to make it easy. Okay? So we could say by definition of odd, the original is valid. Okay. So that's why, and Mr. Rover, when you suggested like we don't have to write that like after each case, I was just being lazy so that way we could hold it off to the end, so that way we can save ourselves a little bit of writer's
Well,
cramp.
I knew you'd have to write it again.
That's correct, at some point, right. Okay. So guys, this is the division into cases, and what you guys are finding out is that it's not difficult, it's just a pain in the ass, okay? Because you're basically just doing the same stuff we already know again, okay? All right, questions I can answer before we try another one. Okay, so a secondary example. Okay. I want to prove that the sum of 4 consecutive integers is always even. Okay. Again, what you might wish to do is just pick 4 integers, add them up, and consecutive integers, excuse me, and make sure that it does work out. Because you don't want to go through and prove this and not have it work. Okay, so just off to the side really quick, I'm just going to write this. You guys don't have to copy it. Let's say 10, 11, 12, 13. Okay, those are 4 consecutive integers. Nobody doubts that. Okay, 22, 33, 46. That's even, right, guys? Okay. Let's just say I started with an odd number this time, right? Because so I can either start with an odd number, or I can just do 1 plus 2 plus 3 plus 4. That's going to be equal to 10, right, guys? And that's even. Right. So at least if and remember, guys, that's the 2 possibilities. We can either start with an even number or start with an odd number, right? Guys, isn't it fairly obvious that if I start with an even or if I start with an odd, it's going to eventually end up being some sort of even sum for this, okay? So now it's our job to prove that for any variable, or I'm sorry, for any 4 consecutive integers, okay? All right, so everybody understands what we're trying to prove first of all. Okay, so let's go ahead and prove it. Okay, so we just need 1 integer for this case, okay? So let's start by saying let's let x be an element of the integers, okay? I'll put in brackets x arbitrary but particular. And that's all we know. Okay, we didn't say that x was even, odd, perfect square, anything like that. Okay. So it would lead us to believe that the easiest way to try to prove this might be even or odd. Okay, so let's try even or odd. Why not? Okay, so case 1. Let's let x be an element of z even. Because remember, guys, the only 2 outcomes for this is if the first integer is even or if the first integer is odd, right? There's no other way that you can write 4 consecutive integers, okay? Regardless of what those integers are, okay? So, we already let x be an element of z even, okay? By definition of even, we can say that x is equal to 2k, where k is an integer. easy, right? We've done that literally dozens of times. Now we have to do a substitution step, right guys? So, if in terms of x, okay, so now we're going to do by substitution. How do we write the sum of 4 consecutive integers in terms of x, not in terms of k? Right?
X plus 1 plus x plus 2 plus x plus 3.
So, x plus 1 plus quantity x plus 2 plus x plus 3, right guys? That's 4 consecutive integers, right guys? And that's it doesn't matter what the first one is, and that is the sum of 4 consecutive integers. So think of the first number being 10. 10, 10 plus 1, 10 plus 2, 10 plus 3. Okay, does that make sense to everybody as to how we define consecutive integers? Not too difficult. Okay. By substitution, doesn't this become 2k plus 2k plus 1 plus 2k plus 2 plus 2k plus 3, right guys? That's all it is by substitution. Okay. Hopefully that doesn't hurt anybody's feelings. Donnie, does that hurt your feelings? Oh, darn. Not that I care if your feelings were hurt. Alright. What seems like the next most obvious thing to do at this point, guys?
Addition.
Combine like terms. Isn't this thing just beating you upside the head? We got so many k's and so many constants in there, let's just combine them. Okay? So we have some like terms. By combining like terms, 2k, 2k, 2k is 8k. And then by combining constants, 1 plus 2 plus 3 is 6. What are we trying to show about this thing?
It's even.
It's even, right? So what can we do with 8k plus 6?
Take a factor.
Factor it 2, and we're done, right? I mean, this one's really easy. 2, 4k plus 3, just by factoring a GCF, which is going to be equal to 2p, right guys? Or whatever letter you want to use. I'm just going to use p consistently, so that way when you guys are doing your homework, makes it really easy for you guys, so that way you don't try to figure out or utilize some other letter. Okay, so this is our GCF, and then this guy's by our integer closure. Okay, and of course we want to make sure that who's ever looking at this knows that P is not a vector space of magnitude 5 by 7. All right, it's just an integer. Okay. So there we go, right guys? Nice and easy. This one's actually a little bit easier than the previous one, okay? As long as we know our definition of consecutive integers. Okay? So what's the bad news, guys? Yeah, we gotta do case 2, right guys? All right, but that's okay. Usually, once you get case 1, case 2 is the same thing. You just plug in some different stuff. Okay, so let's go ahead and do case 2. Okay. So case 2. Let's let x be an element of Z odd. By definition of odd, x is going to be equal to 2k plus 1, where k is an integer. So that's easy, we know that. And guys, isn't it the exact same steps? We just set up the consecutive integers, we substitute, we collect like terms, hopefully we can factor out a 2. Okay, so basically guys, it's going to be very easy to do the rest of it. Okay, so by substitution, plus x plus 1 plus x plus 2 plus x plus 3, quantity, sorry, is going to be equal to 2k plus 1 plus quantity 2k plus 2. If you want to write 2k plus 1, that's fine too. You could just go ahead and just squish it together. Just make it really easy on yourself. Okay. Plus quantity 2k plus 3 plus quantity 2k plus 4. So, everybody good with that, guys? Any questions? Okay, just substitution. There's a little bit of computation in there, but don't even sweat that. Okay. Just like the previous step, doesn't it seem obvious that what we should probably do is collect like terms, make this beast into something that's manageable? Okay, so we're going to combine some like terms. So by combining like terms, I think we get 8k plus 10 this time, as opposed to 8k plus 6. All right. And then clearly we can factor out a 2 and use closure, and we'd be done. Okay. So that's equal to 2 quantity 4k plus 5, which is equal to 2p, where p is an integer. Okay. GCF closure. All right, so let me leave this up here for a minute, let you guys copy all that down, and give you an opportunity to ask some questions if you have some. Okay. Anything I can answer for you guys, or algebra stuff okay? Not too difficult algebra stuff, a little bit sneaky sometimes, but this one's pretty straightforward. Okay guys, the good news is that now we're done with this. We just need the wrap-up statement. So we can just say by case 1, case 2, we could say that x plus 1 plus x plus 2 plus x plus 3 is equal to 2p. So let me write that out. So thus, by case 1 and case 2, x plus 1 plus x plus 2 plus x plus 3 is equal to 2p. Okay. And we proved that in the previous two. Okay, I mean, it's so obvious that we've already proved it, it hurts. Okay. So by definition of even, the original statement is true. So by definition of even, the original statement is true. All right. So the good news is that on the exam, I'm only going to give you guys like 10 or 15 division into cases proofs. I'm kidding. That's probably one. All right. Did I scare anybody for a second?
That was like really good.
It still takes forever to write it out.
Yeah.
Yeah. It's simple. I know what you mean. No, there's no time. Yeah. So, okay. All right. What do we think, guys? Any questions I can answer so far about the division into cases? It's not difficult. Okay. And again, it's really cool because this is a tie to some of the things you guys might remember from calculus, or maybe not remember, regardless. But at least I can show you guys like somewhere you guys have learned something and you can use it. Okay. Now, remember beginning class we did division into cases and we used the quotient-remainder theorem. And I said, okay, we're eventually going to get to a topic to where we can actually implement this division into cases and the quotient-remainder theorem. Okay. So, let's go ahead and prove an example utilizing the quotient-remainder theorem. Okay. So, what I want to do is I want to prove that the square of an integer has the form 3k or 3k plus 1. Okay. And I want to use the quotient-remainder theorem using d equals 3. Okay. Now, let's think about like why this might be important to a computer program. Okay. If you're a computer, okay, just pretend for a second you're a computer, all right? You don't know the definition of even. You don't know the you don't know the definition of a perfect square, right? You have to have some way to tell if a number's a perfect square. Okay. So, if a perfect square, if a number doesn't fit this form, it's automatically not a perfect square, okay? Like for instance, okay, I'm trying to think of a number that's not a perfect square that probably wouldn't fit that form, okay? Maybe something like 21, well no, 21 works, but 23, okay? Guys, if you were to use the quotient-remainder theorem, okay, with d equals 3, okay, wouldn't that be equal to 3 times 7 plus 2, right? What can a computer automatically say about the number 23? Not a perfect square, right? So, for some reason, if a computer can figure this out, okay, then it says right away it's not a perfect square. Now, there are some numbers that kind of go against the grain for that. Like, for example, if I gave you guys 24, wouldn't that be 3 times 8? And a computer might confuse that with being a perfect square, because it says it either has the form 3k or 3k plus 1. So this isn't the only test that a computer might use to determine if a number is a perfect square, but it's along the same lines. Okay? Now, somebody go ahead and throw out a perfect square for me. Be nice.
25.
25? Okay. Isn't 25 equal to 3 times 8 plus 1? It fits the form 3k plus 1. So give me another one, please. 16? In stereo, nice. 16 is equal to 3 times 5 plus 1. Fits the form. Okay. How about, I don't know, 169, right? That's a perfect square. That's 13 squared. So that's going to be, shit. 3 times, what do we have here? 56 plus 1. Okay, thanks. I was getting there. Guys, they all fit a perfect square form. Even something like 0, right? 0 is a perfect square.
3 times 0.
3 times 0 plus 0, right? So all of these perfect squares look like they fit this form. Okay? Now it's our job to be able to prove that statement. Okay? So does anybody see like why somebody might actually want to use the quotient-remainder theorem in real life? Okay, it actually does hold some sort of value to people. Okay, not just to us, but like people that like to program stuff. Okay, so let's go ahead and prove this. Okay, and by the way, if d equals 3, somebody remind me, what are the different outcomes that could occur if d equals 3?
0 on 2.
We'd only have 3. Do you remember what they look like, sir? If not, that's okay.
3 times 0 and
3q plus 0, 3q plus 1, 3q plus 2. Perfect. Like it was up there, it was just coming out. Good. That's very nice. So guys, wouldn't we have 3 cases for this problem? Okay. Fortunately, I didn't let d be equal to 16, because that means there would be 16 cases. Okay, so let's start by saying, let's let, we can just say x, it doesn't matter, be an element of the integers. Okay. Where x is equal to dq plus r with d equal to 3, okay, and 0 less than or equal to r less than d, and we should also make sure that we define r and d to be integers as well. So basically, guys, all we're doing is we're just utilizing the quotient-remainder theorem here, right, guys? That's all we did at the beginning of class. Okay. We can also say by the quotient-remainder theorem, and I'm going to put this in brackets because we don't necessarily need to write this. Okay. So, by quotient-remainder theorem, okay, Mr. Williams, you're absolutely correct. There's 3 possible outcomes. X could be equal to 3k, 3k plus 1, 3k plus 2. Okay, and then since that's a comment, we don't have to define what k is. Okay. But I'm just saying this like just in case you have a problem like this at home, okay, for your homework, and that this might be helpful for you guys to remember how we define those. Okay, not saying you have to write it, okay, but it might be helpful for you guys to think about where this is coming from. Okay. So, everybody good with the definitions? That's pretty easy, right, guys? Okay, so we have case 1. Okay. Case 1, let's let x be equal to 3k, where k is an integer. So now we have to define k as an integer, because it's no longer in the comments field, if you would. Okay. Next thing we do is substitution, right guys? We define the variable, we use substitution. So by substitution, what are we substituting into?
Either of them, 3k or 3k plus 1.
Unfortunately not R. Good try. Because that's what we want to end up with.
Oh, and that
X squared.
Okay, we're going to substitute into x squared, right guys?
square, okay. Yeah.
Because aren't we trying to show that the square of some integer has the form 3k or 3k plus 1? Okay, so by substitution, x squared, since x is equal to 3k, is equal to 3k quantity squared. Go ahead, John.
I'm going back to the first thing real quick, where you define R and D as integers. Isn't it Q and R, not R and D?
Hold on a sec. Yeah, it should be. You're right, because we've already defined D to be 3 constant. So yeah. Sorry about that. I'm just making sure. You're correct, John. Sorry. Tactical error on my part. Just take a half point off of my proof there. So now I'm down to 9.5 points. Oops. Or you just write in the teacher evaluation. Doesn't know the difference between a D and a Q. Sorry about that, guys. But good catch. Thank you, sir. Okay. What seems like the most obvious thing to do at this point, guys? Yep, just expand it to 9k squared. Good. Okay. And we'll write in the steps after we're done here. What are we trying to show that 9k squared is equal to?
3k,
Or,
3k plus 1.
right, one of the two forms, right? Doesn't it look like it's going to fit the form of 3k?
Yeah.
All right, so how do we make it look like 3k?
Take a
Is that
square
right?
Factor out 3.
Yeah, we could just write it as 3 quantity 3k squared, just by a common factor there, or just by computation if you would. And then guys, don't we know that 3k quantity squared, or quantity 3k squared is just like a p or something like that?
Yeah.
So that's going to be equal to 3p, where p is an integer. Okay. Like I said, I'm going to write the steps in a second. Right? But does that make sense, guys? We need to show it fits one of these two forms. It doesn't matter which form it fits. It just has to fit one of those two. Okay. If I were to fill in the steps, multiplication, factoring, closure. And there we go. We're done with case 1. Okay. Yeah, me too. The bad news is that we still have to do case 2 and case 3. Okay. So case 2 is going to be basically the same thing, except this time we let x be equal to 3k plus 1. And again, what we're doing is we're just exhausting all the possible outcomes from the quotient-remainder theorem. Okay. So we're basically utilizing some of the stuff we did on the first test with exhaustion, except we're doing it at a much higher level. Okay. So for case 2, yep, I can and I will. Is that good, John?
Yes.
Okay. Yeah. By the way, guys, if I'm going too fast, let me know. I'll slow down. So, case 2. I know I get all happy about this stuff and I start writing quickly. So this time, let's let x be equal to 3k plus 1. Okay. Oh, go ahead, Rob.
And where are we getting these substitutions?
These are coming from the quotient-remainder theorem. So remember when we defined that the possible outcomes when d equals 3 is either 3k, 3k plus 1, or 3k
So
plus 2.
under 3Ks.
Correct, right.
And,
Go ahead.
and why do we use 3's D?
Oh, because what I said was, prove that the square of any integer is 3k or 3k plus 1, and I just gave you the hint to do it. Okay.
Gotcha.
I'll try to give you guys hints where, like in real life, you just have to basically think to yourself, how can I get to that form, okay? But in math life, I'll give you the hint. We'll see. Okay, does that help out a little bit, Ryan?
Yeah.
Okay, good question. Okay, so we're going to let x be equal to 3k plus 1. We're going to substitute. So by substitution, we can say that x squared is going to be equal to quantity 3k plus 1 squared. Okay. Now, we don't want to use closure. Okay, you don't want to use 3k plus 1 as p, because then you just get p squared, right? You don't get 3p or something like that. So I often see students try to use closure incorrectly right here. While it will get you p squared, it won't get you the form of 3p or 3k plus 1 or something like that. Okay? All right, so what do you guys suggest we do at this point?
Expand.
Go ahead, James.
Multiply it out.
Yeah, we're just going to FOIL it out, right? Okay? So if you guys go ahead and use your FOIL, that's not going to be 9k squared plus 1, right guys? So remember, it's a binomial. And if you don't know what it equals to, you just go off to the side and do it. Okay? But correct me if I'm wrong, 9k squared plus 6k plus 1. Okay. Does that look good to everybody just by using the a plus 2ab, a squared plus 2ab plus b squared? And again, if you can't see that, okay, better be right, just do this off to the side. Okay, just do 3k plus 1, 3k plus 1, 9k squared plus 3k plus 3k plus 1, 9k squared plus 6k plus 1. Okay? So, I don't want to see anybody doing like the freshman's dream where you think you can just distribute the square through there. Alright? Don't ever do that. Alright? If you ever did that in your life, hopefully your teacher yelled at you for doing that. Alright. So, what do we do at this point, guys, now that we have this form? Yeah, GCF of 2, right, Donnie? In the first two. Okay? So, if you factor that out, or sorry, GCF of 3, done. Yeah, it would kind of hard to be factored out of 2 from that, because then we get some fractions. Not saying you couldn't, but you wouldn't. So 3k squared plus 2k plus 1. Okay, good. And then guys, what does this equal?
3p.
3p plus 1, right guys? And that's one of the two forms that we wanted to see, right? Remember, it's either 3k or 3k plus 1. So we could write this as 3p plus 1, where p is an integer. Okay.
We can also do 3p too, right?
No,
By closure, you can do 3p?
no sir. Because if you factor out, let's
Oh,
say,
okay, I got you, 130 up there.
if you factor that out, that would be rational. It would no longer be integer closure.
Yeah,
Okay?
got you.
So yeah, you can't use rationals and integers together. They don't play nicely.
Yeah.
Okay? Alright guys. So does that one work for everybody? Any questions so far? Okay. Last one, case 3. Oh yes there is. Yeah. Because remember we said that there was case 3k, 3k plus 1, or 3k plus 2 by that Quotient-Remainder theorem. Okay? So this one actually does have 3 cases. Sorry about that. The good news is you guys only have to do this once. I have to do this for the remainder of my career twice a semester, which is going to be another 30-some years if Social Security holds up. If not, oh, well.
50.
Yeah, I'm screwed. Oh well. That's why they make alcohol. To preserve my liver. That's what I keep telling myself. So we're going to let x equal 3k plus 2. We're going to substitute again. It's basically going to look like the previous one. Okay, so let's just bully it and get it done. Okay, so by substitution, x squared is going to be equal to 3k plus 2 squared. Alright, and then correct me if I'm wrong, if I were to FOIL this out, 9k squared plus 12k plus 4. Not 12 plus 4, 12k. Oh, you suck. Yeah, I'm getting it. Thanks, technology. I forgot the K in there.
On case 2 and case 3, since they are unrelated each cases, shouldn't you mention that K is a...
At the end of the oh, I see what you mean.
You should x equals 2k plus 2, where K is...
Yeah, I forgot to put that in there, didn't I? Thanks, Mr. Weber. So we should say in here that K is an integer, which is why I purposefully let all this space in here.
Right.
Right, exactly.
That
I definitely wouldn't forget anything.
subconscious forethought.
Subconscious, yeah. So thank you, sir. Appreciate that. You're absolutely, yeah. Every time we're in like a local stage, if you would, you want to define an integer. Okay, thank you, sir. All right. So at this point, guys, we can go ahead. We could factor 3 out from the first two. Actually, no, we couldn't yet.
No, 9k squared
We
plus
have to write 4 as 3 plus
Plus
1,
one,
right, guys? Okay. Sneaky, sneaky. So this would be equal to,
9K.
yeah, 9k squared plus 12k plus 3 plus 1.
Now you can factor.
Yeah, now we can factor out that 3.
Now we get.
Now we can write this to 3p plus 1. Mercifully. Okay, so let me let you guys copy that down for a moment.
Why is it 3p plus 1 and not 3p plus 2, like the...
Oh, remember what we're trying to prove, Andre. We're trying to prove it's either 3k or 3k plus 1. That's the original. We substituted 3k plus 2, right?
Why did we substitute 3k plus 2?
Remember we said that D has to be equal to 3, right? And so it's one of those 3 cases that we started with.
Okay, so it's one of the cases where we're trying to prove the original.
Right, we're trying to prove all the way back up at the very, very beginning, okay? Right, because I do see that often, or not often, but enough, where somebody will try to prove the substituted part, okay? Just because you're substituting it doesn't mean you actually want to prove that substitution. You want to prove the original, okay? Great.
Would you actually be able to do that? It's like I can almost quite do it. But
Right. You shouldn't be able to prove it's equal to 3k plus 2. And if you can, that means you could have found a counterexample at the beginning, and we just wasted 25 minutes of our lives. Okay? Not saying that some of you guys don't think we've already wasted 25 minutes, but we would have truly wasted 25 minutes. Okay. All right. Is this good, guys? Any questions? We'll finish this out. Okay. So, very last line, we can say thus. X, remember we defined x to be equal to dq plus r. So x is either equal to, or thus by, sorry. So thus by case 1, 2, or 3, x is equal to, or x squared, correct. So x squared is equal to 3p, or x squared is equal to 3p plus 1.
Why not and?
No, you can't have and, right? Because that means that at the same time, x is equal to 20 and x is equal to 21. And that's impossible. You can't have a singular variable equal to 2 instantiated values simultaneously.
You say it that way.
Right. Okay. Yeah, you have to be careful with that wording. Okay. So now, if you put in by accident, I'd probably scratch it out and say never ever write that again. But I wouldn't take off any credit for it.
mutually exclusive.
Yeah. Or just attach the $20 bill, and then whatever you write will be correct. Okay. That's clearly going to be valid. So thus the original statement is true. Okay. There's nothing else really to show. So thus the original is true. All right. Merciful. All right. So the way I think about the division into cases, I think of it like mowing my lawn. It's not difficult. It's just long and tedious. Okay, I can do it whenever I want. Okay, just whenever I feel like doing it. Okay. All right. Does this make sense, guys? Any questions about division into cases before we look at some floor and ceiling proofs? Okay. All right, guys. So let's just initially look at some of these floor and ceilings. Okay, they're not too difficult. When I talk about a floor function, okay. A floor function might be like something you guys might have heard of, the least integer function. Okay, basically it just chops off it just truncates all the decimal part, and you just go to the next lowest integer. Okay, this is the definition that we're going to be using in our proofs right here. But basically, if we take the floor of x, x has to be between some integer and the integer plus 1. Okay, so that's the definition that we're going to be using at some point. Okay. Same thing with the ceiling function, sometimes ceiling called the greatest integer function. Okay? So greatest integer function n such that n minus 1 is less than x or less than or equal to some other integer n. Okay, so x is a real number, by the way. I don't think we ever defined what x is. So x is just some real
So
number.
for 5, so for the number 5, the floor will be 4.
No, the floor would be 5.
Floor will be
Okay.
5.
The
Okay.
floor of 5 is 5. Okay?
Okay.
Because remember, there exists some number
Yeah.
or some integer n such that it's equal to that integer or between that integer plus 1, but not equal to the integer plus 1.
Okay, so ceiling will be 6 then.
Right, the ceiling of 5 would still be 5. Okay.
So it's a 5.01, like there's a point.
Well, then that would be 6.
6, okay.
Okay? By using our definition. In fact, we're going to look at a couple examples right here of how to execute that. Okay? So, if I was to ask you guys to evaluate or compute floor of 2.001 plus ceiling of 4.997, the least integer from 2.001 would be 2. And then the floor or the ceiling of 4.997 would be 5, right? You would just go up to the next integer, okay? And by multivariable calculus methods, 2 plus 5 is 7, okay? So basically, guys, all you're doing is you're just using basically almost like a step function. That's all it is, okay? So, go
What
ahead.
if the ceiling function is on 2.001?
Then it would be 3. Oh, right. So you're not using rounding conventions. You're just basically saying if there's any decimal part, you just shoot it up to the next floor ceiling. And then for a floor, if there's any decimal point, you just get rid of it. Okay?
This might be a silly question, but how do you determine, oh, it's the symbol that determines whether it's the block.
Right,
I
you
didn't
just-
see that.
No, that's okay. Yeah, they
I
look
thought it
the
was a
same.
bracket.
No, that's okay. Plus, I've been beating you up with math for an hour and 15 minutes, so yeah. Vision's the first thing.
Yeah.
I saw that.
Yeah.
I like blaming you.
That's okay. You can blame it on me. That's fine. Just blame it on me.
Who else would we blame
I don't know. Government, aliens.
Oh, Bala.
Yeah. Oh. Anyway. All right. Ceiling of negative 3.995.
-2.
That's going to be negative 3, right, guys?
Negative 3.
And think of it like a number line, okay? Like for instance, if I was to plot, like if this is negative 3, and this is negative 4, negative 3.995 is right here, right? So wouldn't you want to go up to the next integer, okay? So the next integer up from negative 3.9994995 is going to be negative 3. Right? What about the floor of negative 4.01? Negative 5, right guys? Okay. So think of it like a number line. I'll go over here and do it. If this is negative 4, and this is negative 5, right here would be negative 4.01, right? The next integer down from negative 4 is negative 5. Does that make sense, guys? If you're ever confused, just draw a number line. Okay, makes it really easy. I know it seems like it's really infantile, but it's better than getting it wrong. Okay? So we get negative 3 minus negative 5. Otherwise, minus 2.
You do that complicated algebra.
Something like that, yeah. It's called Catholic school. Alright. Questions I can answer, guys, about this? Not too difficult, right? You just draw a number line, make it easy. Okay. Div and mod functions. Okay, div and mod functions, really nice and easy. Okay. Whenever you guys hear the term div, that's the integer quotient from dividing two integers. So if there's any remainder, you just truncate the remainder. The modulus is the remainder part of the function. Okay, so if you guys are doing a div and a mod, basically all you guys have to do is just find out what the integer is for the division and then figure out what the remainder is. Okay, it's basically like a 3rd grade problem. Okay, so if I asked you to evaluate 94 div 5, okay, what you guys would do is you would literally just do this. Okay, just set it up. Okay. If I was to ask you guys how many times 94 evenly divides into 5, you guys would say it's 18, right? Okay. 18 times 5 is going to give you 90, and the remainder is 4. Okay, so a trip back down memory lane. Of course, we never do that anymore, right, guys? Because we just have calculators that do it for us. But if I was to ask you guys what 94 div 5 is, what would you guys tell me? 18, right? So this guy right here, 18, is going to be 94 div 5. So 94 div 5 is going to be equal to 18. And then if I was to ask you guys for 94 mod 5,
4.
that would be equal to 4, right guys? That's all it is.
That's used a lot in programming.
It absolutely is, okay? James, do you remember an example like when you were programming like maybe comp sci 1 or something like that? Do you remember ever doing a program where the modulus was important? Or does anybody?
Yeah, prime number.
Yes.
Prime numbers, okay? Did anybody ever do like the days of the week problem?
Yep.
There's an algorithm to be able to figure out what day of the week it is based on the modulus, okay? And if you haven't done that problem, go back and hit your computer science teacher.
Change from quarter, change and all.
Yeah, there's all kinds, this is very important, by the way, in computer science, as probably most of you guys have already found out. It probably would have been nice if you took this course first before taking Comp Sci 1, so you could say, oh, okay, now I know what a modulus is, and then use it. So, but you guys probably figured it out on the way while you were there. No? Probably not? Okay, that's all right then, never mind. All right. For letter B, okay, if I have 7 div 40, now be careful with this one. Okay. A lot of students might say that 7 div 40 is 5, but it is not.
0.
It's 0, right? Okay. The reason being is because you can't get any 40s out of 7, right? There's no times that 40 or 7 is divisible by 40. So 7 div 40 is actually 0. Okay. Does that make sense to everybody, guys? The bigger number should go first if it actually is integer division. What does that mean then? That 7 mod 40 would be. It's not 0, but
40.
7.
7?
Okay? Yeah, think about this, okay? If you did 40 divided by 7, right? 0. 0 times 40 is 0.
Oh, 0, okay.
There's your remainder. Okay? So it would be 0, remainder, 7. Okay? 40 wasn't a bad guess. But remember, that's the number that you're actually trying not to divide, that's the number that you're dividing into. It's not how many times you're trying to divide out for. Okay? Alright, so does this make sense, guys? Any questions about div and mod, or any questions about floor and ceiling stuff? Pretty basic stuff, not trying to be too difficult with this. Okay, so we'll stop here for today because I think like these proofs, like they'll at least take 10 minutes, and we only have about 8 minutes left, so, and I'm sure I owe you guys a few minutes here and there, so we'll stop here, okay? See if you guys can get a head start on some of the assignment stuff, assignment number 5, and if you guys have some questions, make sure you guys bring those to me on Wednesday, okay? Alright then, so I will see you all Wednesday, have a splendid rest of the day, and all that good stuff. Go Orioles.